Okay, so basic radical function, y equals root x. So just like y equals x is your basic linear function that we did in Math 10, y equals x squared is your base quadratic function that we did earlier this semester. Y equals root x is your base radical function. And you'll do more with this in Math 30 as well. Base radical function y equals root x is the square root of what kind of number does not exist in the real number system. So what can't you take the square root of? Negative. So here, so the square root of a negative number does not exist in the real number system. The domain of y equals root x is x has to be greater than or equal to 0. Okay. For y equals root x, complete the table of values, sketch the graph, and complete the following statements. So, put 0 in for x, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. Okay, and then plot those. So 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. And it's continuous. You can take the square root of any positive real number. Okay, but we do not put an arrow on this end, right? That's an end point because of the fact that you can't take the root of a negative. So the shape of that should look kind of familiar if you turn your head. So, yep, you turn your head, it looks like half a parabola. Okay, so the shape of the graph is half of a horizontal parabola. You look at it this way, that's the left arm. 1 unit over is 1 up, looking this way. 2 units over is 2 up, and it would be the same over on this side if we actually graphed it like that. The vertex, so even this, though this doesn't continue this way, it's still called a vertex. There's no arrow on it. It's 0, 0. And the range for this is everything greater than or equal to 0. Okay, because that arrow is going up and to the right. So range is all values of y, where y is greater than or equal to 0. So really the domain and range are the same for this radical function, the base function. If you do transformations, then obviously it's going to be a little bit different. All right, so now we're going to do some transformations, just like we did for parabolas, for vertical parabolas. So all the transformations, including stretches, reflections, and translations that you previously learned, can be applied to radical functions. Use your transformation skills to complete the following. So it says, complete the table by describing the transformation that was made to the original base graph. The base graph is shown. Sketch each of these transformation functions. So, remember, back to quadratics, if you had y equals x squared, that was your base graph. If you had y equals x minus 2 squared, that moved the vertex 2 to the right. It was a horizontal translation. Well, that's what we're doing here. We're replacing x with x minus 2. So this is a horizontal translation 2 units right. Notice how I am abbreviating that. Please don't abbreviate during a test. I just did it for the chart. Okay. So if we were to graph that, you take every point and move 2 to the right. So the vertex will become 2, 0. Kind of like if we had x minus 2 squared for a vertical parabola, the vertex was 2, 0. Same deal. This point here, 2 to the right. This point here. So choose all the nice values. And that
in front of his face. Okay. So it's going to have the same shape, just everything's moved. Next one, notice how the -2 is outside the radical. So that means your original graph, now we're subtracting 2 from every y value. So that's a vertical translation, 2 units down. So from our original, our vertex now is going to be 0, -2. Okay, so then each nice point, go down 2. Again, the shape is not going to change. It's just a different location. So I'm kind of color coding it. Now, next one, that's saying we're taking our original y value and we're multiplying it by 1/2. So anytime you're multiplying, it's a stretch. If it's outside of the original function, then it's a vertical. So vertical stretch by a factor of 1/2 about the x-axis. Okay. So now we take our original y values and we multiply them by 1/2. So y value of 0 stays at 0. Okay, now our shape is going to change. Y value of 1 times 1/2 is 1/2. Y value of 2 times 1/2 is 1. Y value of 3 times 1/2 is 3/2. Y value of 4 times 1/2 is 2. So it's kind of going to be flatter. Okay. Next one, there's no numbers, but there's a negative in front of the radical, so that means your original y values, we multiply by -1. That means you're changing your y values. They're changing from positives to negatives because they're all positives to start. So here, this is a reflection in the x-axis. Okay. So your original y value 0 stays. 1 becomes -1. 2 becomes -2. 3 becomes -3. 4 becomes -4. So really that purple and the original black graph form parabola, like we spent a lot of time talking about earlier this semester, but just on its side. Okay. And then the last one is a vertical, so we have to stretch and reflect separately. So this is a vertical stretch by a factor of 2 about the x-axis, and then a reflection in the x-axis. Now, when you do this, though, you can find the new point all at once. Okay, so it's a vertical stretch by a factor of 2 about the x-axis, and then a reflection in the x-axis. Really, you're taking your original y value and multiplying by -2. So 0 times -2 is 0. 1 times -2 is -2. 2 times -2 is -4. 3 times -2 is -6. and then we're going to run out of space. It's going to look something like that. Now there are, we didn't do any horizontal stretches, but really think about if I gave you y equals square root of 4x, that is a horizontal stretch by 1/4 when it's inside. We haven't done a whole lot of horizontal stretches, but that's the same as 2 root x. So with radicals, you can actually always show it as a vertical stretch, which is really mostly what we've learned. In Math 30, you'll do more, all horizontal, vertical, all that kind of stuff. But this is the same as this. So just realize a horizontal stretch can be a vertical for a radical function, okay? And for a quadratic, because of that symmetry that they have. But you're not going to have to worry too much about that, all right? So that's graphing. Now we're going to put it all together. So there's f of x. So -2, square root of x plus 1 plus 4. So state the transformations in the correct order. And then we're going to graph it. So always remember stretches, reflections, and then translations. If you don't put them in that order, you're not going to get full marks. Okay? Even if it doesn't matter, like a vertical stretch and a reflection, it's not going to change your graph, but I still want it in the correct order because next year it will matter for a lot of functions. So here, look at the number in front of the square root. It's a -2, so that means it's a vertical stretch by a factor of 2 about the x-axis. Then it's a reflection in the x-axis. So we've done that first, then the negative, and then we've just got translations. Doesn't matter which order you do the translations. So we could do vertical translation up 4 units, okay, because it's plus 4. And then horizontal translation, remember it's the opposite of what you would think. So if this is plus 1, it's left 1 unit. It makes sense when we were finding the vertex of our parabolas. If it was x plus 1 in the brackets, our x value at the vertex was -1. Same thing here. Okay, so when you're graphing this, you can go through and do a graph for each transformation. That's how we started parabolas. But then we realized we don't have to do that. We can find our new vertex, okay, right away. That's just from the translations. And then think about the shape of our graph from that point. So that's what you can think about doing here. So our vertex is going to be -1, 4. -1, 4, -1, 4. So here, that's going to be up there. Okay. Now, if it was just that, then our graph would look something like that, right? Going through there. Okay. But we have to have stretched it. Technically, we have to do that first, but from this vertex, we just have to draw a stretched graph, okay? So think about if you've stretched it by a factor of 2 vertically, that means for 1 unit over, I'm just going to erase this now. 1 unit over is normally 1 up. Now it would be 2 up from there, and then it's reflected, so it would really be 2 down from the vertex. So 1 unit over is going to be 2 down because of the negative 2. 2 units, I should do 4 units over is normally 2 up. So now 4 units over is going to be 2 times negative 2 is negative 4. Okay, so you're thinking about what the shape would be from the vertex if you did that stretching and reflecting in the correct order. But I'm not doing step by step because then you'll have to draw like 4 graphs if you do that. Then normally for your base graph, 9 units over is 3 up, but multiplied by negative 2 would be negative 6 down from there. So from the vertex, 9 over will be negative 6 down from there. Then 16 is 4 up. 4 times negative 2 is negative 8. From there, so that would be at 15. And negative 8 would be down negative 4 here. No, what did I just do? Did I do this one? Just set that 3 times negative 2 is negative 6. Yeah, so this should be down here. And then this is here. Okay, so, oops, no, something weird happened. Just give me a second. Oh yeah, from the vertex. So here, this was, 16 is normally 4. 4 times negative 2 is negative 8. So from here, 16 to the right would be here. Negative 8 would be 1, 2, 3, 4. Yeah, that's right. What did I just do now? Okay, so 4 is negative 4. So 4 to the right, negative 4. Good. 9 is 3. 3 times negative 2 is negative 6. So 9 to the right, 4, negative 2. There. I think I had it right before. There we go. Okay. There we go. Okay, now get out your calculator. Let's graph it so that you can check. All right, so here, negative 2 square root, I have to use this old calculator, but it's okay. X plus 1, close bracket on that, plus 4. And our window, this is going from what, negative 2 to 16 by ones, to enter twice every time. Negative 6 to 5, let's do. Oh. Okay, the graph. Okay, so if this was on a test and you had to graph, test some of your points. So I think one of my points is 8, negative 2. So trace 8, negative 2. Good stuff. I think my vertex is negative 1, 4. Trace negative 1, 4. And it's flashing on the vertex. Okay, so just test a few points. Then find the domain and range. Okay, so domain here, everything greater than or equal to negative 1. Okay, really, That's all that we're concerned about. We know that we can only take a square root of something that's greater than or equal to 0. So x plus 1 has to be greater than or equal to 0, so x has to be greater than or equal to -1. You don't even have to look at the graph. Then for the range, this, the smallest value you can get for this is 0. -2 times 0 is 0. And so your important point there is 4 for y. So you might have y and 4. What is it? Is it going to be greater than or equal to 4 or less than or equal to 4? That depends on the reflection. So this has been reflected, so it's going to now be going down and to the right, which means it's going to be less than or equal to 4. So this value in your domain comes from there. This value comes from there. And then the direction of the inequality depends on whether it's been reflected or not. Okay. All right, so then image points. So it says the point 25, 5 lies on the original graph. Makes sense. The square root of 25 is 5. Determine its corresponding image point on this new function. Okay, verify algebraically. So this is the one that we just graphed. So we want to take 25, 5 and perform the transformations on it. You don't just substitute 25 into this new graph, okay, a new function. It won't be the image point. It'll give you a point on the new graph, but it won't give you the image point, okay, because the x value will still be 25. So here, if we go through our transformations, a vertical stretch by a factor of 2 means we take the original y value and multiply it by 2. So vertical stretch by 2. Then reflection in the x-axis makes that 10, -10. Okay. Then translate 1 unit left would mean subtract 1 from 25. So translate 1 left. And then from here up 4, so 24, -6. Okay. Now, to verify algebraically, set up a t-chart. This is your y value, which would be -6. Your right-hand side is -2. 24 plus 1 underneath the radical plus 4. So 24 plus 1 is 25. Root of 25 is 5. -10 plus 4 equals -6. Okay, so your left side equals your right side. Then algebraically determining the x and y intercepts. Excuse me. So y-intercept's really easy. Y-intercept is when x equals 0. So in this case, we're going to substitute 0 in for x. So -2 times 1 is -2 plus 4 is 2. So that's your y-intercept. Okay, and take a look at your graph. Y-intercept is 2. Looks correct. X-intercept is when y equals 0. So 0 equals -2, x plus 1 plus 4. So this is really going to lead us in to our next lesson, which is solving radical equations algebraically. Because we have a square root in this. So just like we did for quadratics, we wanted to get the squared term by itself, wherever the x was. So here, we want to subtract 4. So we'll get negative 4 equals negative 2 root of x plus 1. And then divide by negative 2. And then square both sides. And then solve for x. Okay. With these, you do want to verify. Sometimes you get extraneous solutions. So we have our graph. So that is a quick way of verifying. That's what we got our x-intercept to be, was 3. So we know it's correct. Algebraically, to verify, we just put it into our back into our equation here. So we would have 0 here, negative 2, 3 plus 1 plus 4. Okay, so we know it works. There are some radical equations that will have extraneous, not when it's just a radical function like this and you're finding x and y intercepts. Not usually anyway. Okay, so that's the end of that lesson.